In this video, we'll look at the relative stability and therefore reactivity of the acid derivatives. So, first things first, if something is more stable, then it's going to be less reactive. Okay, if it's stable as it is, it's going to be less reactive. And there are two main things that are going to determine how stable and reactive a species is. One is its resonance stability. So we're going to look at the different resonance structures for each of the derivatives. And two is how good of a leaving group each of them has. In order for it to react, one of the ends is going to act as a leaving group. And so how good that leaving group is has a lot to do with how reactive that species is. So if we look at our generic derivatives, we've got an acid chloride, the anhydride, the ester, and the amide. So for a reaction to take place, something has to leave. In all of these cases, the group adjacent to the carbonyl compound will leave. So these groups that I'm circling here would be our leaving groups, which means that we would have Cl- as a leaving group in this reaction. We would have this acetate-like ion here. Now, this guy is resonance stabilized because that charge can be shared over those two oxygens because they're adjacent to one another. Here I would have OR minus, and here I would have NH2 or NR2 minus. So in terms of leaving group ability, generally larger something is, more electronegative, the better the leaving group, and then resonance stabilization can help a lot with that. The acid chloride has the best leaving group here because it's got a large electronegative atom. So this is my best leaving group. If we think about acid-base stuff back from general chemistry, HCl is a strong acid, Cl- is a very weak base, it's not reactive, so that's my best leaving group, okay? And then second best is going to be this resonance stabilized carboxylate type ion, okay? I've got an oxygen that's sharing the charge over two oxygens. Next up then, I've got my OR minus. Oxygen with the charge stabilized on only one oxygen is going to be less stable and therefore more reactive than the carboxylate ion number 2. And lastly, I've got this NH2 minus. That's going to be very unstable. It's a small, less electronegative atom with a full negative charge on it. So this is going to be a very poor leaving group for that reason. So I'll write small, less electronegative. The main factor here is resonance, and here we have a large atom that is somewhat electronegative. So the best leaving group is the chloride, and therefore it's going to be the most reactive because the leaving group leaves the most easily. The other factor is the inherent resonance stability of the compound itself. So we've already seen that the acid chloride has the best leaving group. If we think about what all of these carbonyl compounds can do, they can have this charge-separated species with a positive charge on the carbon and the negative charge on the oxygen. Chlorine is a really poor resonance contributor. So even though we could draw a resonance structure like this, it's very unlikely. And so chlorine is doing little to stabilize in this resonance structure, and as a result, this acid chloride has less resonance stability. So we'll write poor resonance contributor. Chlorine is electronegative and less able to share the electrons. So it has low resonance stability. do that. So inherently, chlorine is the best leaving group because it's a large electronegative atom that can handle the charge. And it also provides the least stability to the compound itself. And that's what makes the acid chloride the most reactive of the acid intermediates. Or excuse me, the acid derivatives. Next up, we can think of the anhydride. The anhydride has a decent leaving group because it is resonance stabilized. If we think about resonance here, we can again get this charge separated species. And then we have an oxygen next door that can lend electrons. But what ends up happening here is we have this positive charge next to a partial positive on the carbonyl carbon that's next door to it. So this is going to be a repulsive force. And it's going to be a negative contributor. So this is going to, again, be a minor contributor because of that repulsive force of the partial positive and the positive next door to one another. And so the inherent stability offered by this group here is not that big. So between having less resonance stability and having a decent leaving group in that resonance stabilized ion, this is going to be of intermediate reactivity. So this is the second most reactive. So then we have the ester, which looks like this, generically. Again, charge-separated species, where I've got O minus, and then the carbon with the positive charge. And I have this oxygen next door, which, like with the anhydride, can stabilize. But what happens this time is I have an oxygen with a positive charge, but then I have a carbon next door, and it has it's less electronegative, so it's going to push electron density towards that oxygen with the positive charge and stabilize it. So this is more stable, and it's a better contributor than any of the ones that we've seen so far. So there is more inherent stability in the ester, and we also have a poorer leaving group, so this is going to be less reactive than the acid chloride and the anhydride. So lastly, we have the amide. And I'm going to put two R groups on the amide here. So again, charge-separated compound. And the nitrogen has a lone pair that it can donate to that bond. And now there's a couple things going on. First, the nitrogen is less electronegative than oxygen, so it's going to be less destabilized by the positive charge. It can also have up to 2 carbon groups on it, which send electrons towards the positively charged nitrogen via induction. Just squeeze that on there. And so this is going to be stable. In fact, this bond has significant double bond character. So if we measure that bond, it's actually shorter than a single bond because there is a considerable amount of time spent in this bottom resonance structure. This is going to be the most stable derivative. It has the most inherent resonance stability because that less electronegative nitrogen is able to donate electron density, and that is further stabilized by induction from the R groups on the nitrogen if you have carbons there. And also the nitrogen is the poorest leaving group, being a small, less electronegative atom. So the two things we looked at is leaving group ability, how stable is the leaving group, and then inherent resonance stability. What type of a resonance contributor is that X group coming off of the carbonyl compound? The acid chloride is the best leaving group, the chlorine, with the least resonance contribution. And the amide is the most stable, so least reactive, because it has the most resonance contribution from the nitrogen, and it's the poorest leaving group.